Hi together. In this tutorial video I'm going to show you how to set up an impeller blade geometry from scratch. First of all, we start with the hub contour. So we create a point and create another point, copy and paste, drag it to another position. And then we select the points and create an F-spline curve. So we are in the Y-plane. We create a smooth curve, put everything into a scope and call this our hub. And then we just simply copy and paste everything and rename the scope. Call it shroud. This is the second contour. Again, in the Y-plane we put it a little bit upwards and maybe adjust it a little bit. Usually we would introduce some parameters for this contours, but we keep it easy. Okay, so now we need to have some locations for our leading edge position. So this is a point on the curve, on the hub curve, and we just move it a little bit forward, and we create a second curve point, and this is for the trailing edge. And again we move this curve parameter a little bit so that the point appears at the end of the curve. And we do the same for the shroud contour as well. Just have the leading edge position here, select the curve, create another point and change the curve position on this curve. So then it's, maybe we rename it. So then we have these 2 points and create a connection in between. Again, this is the Y-plane. Blade design is always in the Y-plane. And we can have a tangent value here. And again, maybe shift the start position maybe a little bit. Yeah, adjust the tangent angle again. Okay, so that's our leading edge guide, so to say. We put it again into a separate scope. And maybe we call this stacking. We can do a similar thing for the trailing edge guide. Just put everything into a separate scope as well. So then we have the 2D contours of our device, of our impeller. So now there comes the interesting part. We use this impeller camber curve here. Actually, this is a small feature that just takes some information of the device, like hub and shroud contours and some camber information. That's a 2D camber curve here that is used internally. And we have a specific radius. Enter the guides here. And you can already see this is a 3D curve now. This is a test curve here. And we can also switch between the different representations. We can also have a global theta angle here to rotate. So once again, in order to create such a 3D curve that we have seen, we simply need to have the hub and shroud contours, 2D curves, and then we need the stacking axis, leading edge and trailing edge, but also we need a specific radius location for this curve. And in addition we need some mean camber definition, so we have a function that is within this feature. So it's a smooth curve, and it's in a specific system. We call it beta or theta system. And with this you can create the 3D curve that we call stream section in CAESES. So yeah, the stream section curve, the 3D curve, has two different modes for the camber data. So the first one is the tether or M prime tether system, and the second one is the M prime beta system. And you can basically use any kind of curve to describe the camber. So in this case, I think it's internally there is an F-spline used for this purpose that I'm going to show you in a second. And yeah, so you set this mode and you set the curve, and you can optionally set a factor for the camber data, because often it's modeled in the normalized system. And then we maybe can take a quick look into the feature definition that we have been using. So you can see all this input here. We get the value at start and end and the tangent angles for our camber curve for the function, and we involve these values here for our F-spline curve, and we have a factor. And then in the end there's just a stream section curve that where we set all this information. Yeah, so let's put this camber curve into a scope now. As mentioned before, this is only a test curve, so that we can check whether everything works fine. So from this, now we want to create a surface, and an intermediate step is that we create a curve engine. That's you can see it as some kind of curve generator in radial direction, and we put in some constant values for the time being here for the camber start and end position. And yeah, again we add all the information that is needed for our stream section. Up and shroud. Yep. So actually you cannot see anything right now. It's just an engine that will create our curves in the next step. And for the radius we want to have not a constant value but rather a graph. And this is also a bit specific in CAESES. So we create a function, a linear function for the radius. We're gonna run from the minimum to the maximum radius of the blade, and so therefore we have to set this minimum and maximum value. So we model this function in the XY plane, and we just grab the X position of our stacking axis start location. So this is actually also the radius, and for the end position as well, right? Okay. So then we just simply take this curve and add it in there, so we don't have a constant radius right now anymore, but rather a function for the radius, and from this we can then simply create a meta surface. There you go. As you can see, I'm always trying to give good names and to set up a good structure of my project. So the next step is that we want to create another surface where we apply some thickness, and this surface will be based on this camber surface that we have just created. So we pick this camber surface, and again we have a feature for this purpose, so we can test this very quickly. And as you can see, there is some thickness already applied. There's an ellipse factor that we can change, so now we have a circular shape here, but you can also change it to a more sharper rounding here. And so this feature works pretty nice. So this is the one that we want to use for surface generation. Again, we give good names here. This will be our blade. So I guess you remember from the camber surface that our next step was to create a curve engine. So we pick another definition now. That's the impeller section. And once again, we set the same things again. Here for our thickness, maybe we take a constant value for the time being. And we take a constant ellipse factor. Call this engine. Put it in there. And for our sweep parameter is in the domain of the camber surface. That's also a bit special in CAESES. We have UV surfaces, and this is a function here that runs in the parameter domain of the surface. So with this we can quickly create a 3D surface. So actually this profile runs from the minimum radius to the maximum radius based on the camber surface. And alright, switch on the wireframe. That sometimes helps a little bit. And give a good name. Again, maybe we can choose only 5 sections here. And we can change the thickness. So it's constant thickness at the moment, but we're gonna change it in radial direction in a second. Now that's pretty much it. Also the ellipse factor for the leading edge, it's constant here in this example. Okay, so what's next? So the next step is that I want to create a solid impeller from this blade. And there's also a little piece of functionality here. So we just simply choose the blade surface that we've just created. It's the one here that you can see. Put in the hub contour and the shroud contour as well. And you can see it tries to update immediately. So this is also a recommendation that I can give you, because we are working here with so-called B-reps, and sometimes this is a little bit expensive. So we we just switch off the update mechanism and enter all the required input, and then we switch it on back again, and you can see this is our impeller here. And this is also a solid body now, so we can maybe quickly take a look inside. So you can see that's really a nice and solid body. So we can now simply change the number of blades here, and sure, this is still a solid body. So this is quite nice and handy. Again, we give a good name. What else can we do? We can maybe we switch back to one blade. It's a bit quicker. We can activate a hub fillet here. So you see that there is some fillet in this region. We can increase the radius. And you could also create a blade fillet if needed. So it's up to you, and this feature is also can be manipulated by yourself. If you need something else, then just go ahead, take this feature and manipulate everything to your needs. So the next step is that I want to show you how I'm gonna create radial distributions, like function graphs for the parameters of the blade. So in this case, I start with global theta, and I want to rotate the blade a little bit in radial direction. So I create this 2D curve here. It's a function, and it's in the same window. That's maybe a bit something new to you. So we put in this global theta function here, and we can also set a factor to scale it up in y direction in this system. And then you can see that the blade gets rotated according to this function. Maybe set to a linear blade here for a second and back again. So you can see then it's the theta angle is not constant anymore, but we have a function now. And this is basically something that you can do for any parameter of the blade, thickness, ellipse factor, and camber values for the start and end location, which is the leading edge and trailing edge. So it's fully up to you. For instance, thickness. Let's say we want to start with 5 millimeters and go down to 3 millimeters. Then you can see this is the function for this purpose. We use a name filter, and we can set the tangent angles to have a smooth distribution of this function. So we switch back to the 3D view and go to the curve engine and simply use this function instead of a constant value. And the result is that we have not a constant thickness anymore at the leading edge, but like a smooth distribution. Yeah, typically you would introduce some parameters for these minimum and maximum values here in order to maybe even control them in a study. We put the thickness graph into the blade scope, and maybe as a final step we we create a function graph for our camber start values. So we want to change the camber characteristics at the leading edge region, and for this purpose we have this little graph here that we are setting up. So in this video, or in this example, I use a very specific camber definition, which has where one parameter is this start value, and we can create a function for this value. But it's up to you to use any kind of other camber definition. It's you're fully free to set up your own definition. Okay, so in this example I just set this function here at the curve engine again, and so now we have changed the camber distribution in the leading edge area. So maybe we can change the value to see something again. Yeah, it takes a second. Oh, 0.4 corresponds to I think 40 degrees or something like that. So we have a flow angle here, 40 degrees. And that's pretty much it. Yeah, of course, I mean at any point in time you can go back and change the basic curves here, like hub and shroud contours, and so everything is fully parametric and will follow. So you can see that the surface is created and even in real time you can drag around and change all your functions and your contour curves here. So like typically in such a project you would, or in such a model you would introduce parameters, not dragging around in, like the points in the 3D view, but rather introducing some main parameters that are part of your project and that you can change. And you would also link to these parameters wherever you need them. Like for instance here we have this this hub curve here, this point that depends on the radius now, but maybe also the second point is maybe a bit higher, so we set a relative value here, and then it's easy to change this parameter and not to 6 but rather to 60 millimeters, so that everything follows nicely. Okay, all right. I hope you have enjoyed this little tutorial. I think this is everything that I wanted to show you. Yeah, check out the free version on our website, caeses.com. Yeah, bye bye.